So welcome everybody to the next installment of our weekly reading group. Today, really excited to welcome Devichand Budagam. He is a fourth-year undergraduate student of the Department of Computer Science and Engineering at IIT Kharagpur. I'm going to pronounce that terribly as well. Kharagpur, is that roughly correct?
Yeah, it's roughly correct. Yeah.
Okay. Good stuff. So he works in the areas of NLP, agent frameworks, deep learning, and federated learning, mainly focusing on scalability and efficiency of large language models, along with knowledge-infused pre-training of LLMs as well. Today, he's going to be going through his recent paper, Hierarchical Prompting Taxonomy, a universal evaluation framework for large language models. So really excited to welcome you today, Devi. The floor is yours.
First of all, thank you, Daniel, for giving us this opportunity to present my work out here. And before starting out the presentation of the paper, I would like to give a brief intro about me. I'm Devichand, and currently I'm a fourth-year undergraduate student of Department of Computer Science and Engineering at IIT Kharagpur. And I'm also a research assistant at Queen Mary University of London in Distributed Systems Lab, working mainly on federated learning systems. And I'm also a research fellow at Artificial Intelligence Institute of South Carolina, working on knowledge-infused pre-training of LLMs. So yeah, it's great to meet you, everyone. And today, I'm going to present my work, one of my recent works based on hierarchical prompting taxonomy, which is a universal framework for evaluating large language models as well as datasets. So I think let's quickly get started on it. I'm going to present the work Hierarchical Prompting Taxonomy, a universal framework for large language models. And the co-authors along with me are Sankalp KJ, Ashutosh, Kumar, Vinija, Jain, and Aman. And they are from Artificial Intelligence Institute of South Carolina, USA, and Ashutosh is from Rochester Institute of Technology in USA, and Vinija and Aman are from Amazon AI in USA. So yeah, moving forward, let's go to the introduction. So yeah, we are in an era of LLMs. So I think you can daily see so much of work going around LLMs on architectures, on the prompting frameworks, and many things around their applications and use cases. But we should be keeping in mind that whatever the advancements in all these things might come and go, but the proper prompting and assessment of LLM performance across different tasks will be staying. So yeah, with numerous LLMs and expanding contributions from the open source community, thanks to them, task-based assessment is crucial for selecting appropriate LLMs for specific use cases. As whatever rapid advancements as we have seen in the last year, or seen in the last few months, has risen the application of generative AI or LLMs in across many industries and across many tasks. And assessing these LLMs for using them for these tasks or use cases is pretty important, and the way we are going to evaluate these LLMs for using them to solve our tasks is also pretty important. So moving further, let's go to the basic thing of prompting. So prompting is pretty basic. What we are all doing, we are all using ChatGPT, we are all using different kind of models, and we are prompting the models to solve us the task. And evaluation comes in hand, go by hand with prompting. Like we are always evaluating different tasks or different benchmark data sets based on different prompting strategies. So LLMs have rapidly advanced, and on the side by the prompting strategies have been rapidly advanced, list to most prompting, tree of thoughts, graph of thoughts prompting, and chain of thought prompting, along with its derivatives like self-consistency and other prompting techniques. So each prompting has its own advantage, each prompting has its own dominance over some set of tasks, over some set of LLMs. But one cannot really say that this is the best prompting strategy for all kind of tasks or all kind of LLMs. So how are we going to build up a prompting strategy like that? Or can we really build a prompting strategy which is universal? So this is the main agenda, or this is the main thing which our work revolves around. So generally, people do prompt engineering to get superior assessment scores over a task by a specific LLM. So I think prompting and evaluation should not be interleaved. That what I'm trying to say is like they should not be considered as two different tasks or two different entities, but they should be going hand by hand. So yeah, moving further, I have just tried to show you a demo of like what is the flaws or what kind of deficiencies current systems, current prompting techniques have. So I think I have taken a picture of model card from Llama 3 from Hugging Face. So you can see that there are several models mentioned out here like Llama 3 8B, Llama 2 7B, and some more models like of 70 billion parameters. And you can also see that there are benchmark datasets like MMLU and GPQA, human eval. So basically, from this diagram, you can see that all of these benchmarks were evaluated using chain of thought prompting with different few shot examples. So do you think that we need a few shot chain of thought prompting for each and every model to solve a particular task? That's a question we should always have in our mind. Like, if you are going to solve MMLU task using all these five models mentioned out here, do we really need to use five shot chain of thought prompting to solve MMLU for all these five models? Like using the same complex prompt for 8 billion parameter and using the same complex prompt even for a more capable 70 billion parameter is not actually relevant to benchmark the things. So this is how the current industry works on, and this is how people benchmark things and people try to choose the model which fits which fits for the task. So one thing arises here is like, are prompts really tailored for capabilities of LLMs? I guess definitely not. We are definitely not using prompting strategies which are tailored for LLMs, I guess, because we are just picking up one prompting strategy and trying to apply it for all other models and trying to check whether the LLM responds correctly to that prompting strategy or not. But I think that should not be the case. We should be choosing the task first and then tailoring the prompt to the task. And rather than just tailoring the prompt to the task, we should also be uh, making taking into the account how the model will respond to the task. Like Llama 3 8B might be more capable of solving GPQA rather than Llama 370B. Like we really don't know. Like we just can't say by scaling laws that 70 billion parameters will definitely perform better in GPQA solving. So I guess like the capability of an LLM in solving the task should play a role in tailoring the prompt or in designing the prompt. So here comes a defect in the current evaluation strategies and prompting strategies, and this is where based upon our work starts from. And moving further, so yeah, like the previous question which I had raised in the meet. So can we really create a universal prompting strategy? So yeah, like we need to answer ourselves. So, I guess like creating a universal, like first of all, I just want to elaborate a bit more about the universal term here. So what I meant by universal is like, can we really make a prompting strategy or design a prompting strategy which can perform or which can provide superior performance across any task, across any LLM? So I think creating one like that is pretty impossible with different architecture modifications across LLMs and different kind of frameworks employed to train them and different kind of task complexities. So, but one thing we can change out is we can try to create a universal prompting framework rather than a universal prompting strategy. So how do we compare different kind of tasks and different kind of LLMs? So I have just tried to show you that we really can't choose a prompting strategy over one single task and compare different models. In the same manner, I would just like to say that we really can't compare different tasks or like something like we really can't compare the solvability of MMLU and GPQA uh, with with the same prompting strategy employing a single model. So like taking out an example, let's say you were just going to use a three-shot chain of thought prompting to solve MMLU as well as GPQA, and you are just trying to see the performance on Llama 3 8B. So what our argument is that we should not be using three-shot COT both for MMLU and GPQ because we really don't know the capability of Llama 3 8 billion parameters model in solving these tasks. So there is both a horizontal flaw and a vertical flaws. Like there is both a horizontal shift as well as a vertical shift of prompting strategies. So like, how do we overcome this and how do we rectify this? Like I will show it in the further slides. So moving further, so how do we compare the capabilities of different LLMs in solving a task, and how can we make sure that an LLM utilizes the best prompting strategy, uh, like suitable for the task complexity? So I guess we are making out a paradigm shift here. Like until now, like people have evaluated based on prompt-based evaluation, and now we are going to move towards it, move towards task-based evaluation. So I just tried to show this small flowchart out here to give a better understanding. So I guess like generally we start with a prompting strategy, and we have many different data sets related to many different tasks like question answering, reasoning, and translation and whatnot, summarization. And we try to employ the prompting strategy or give the prompt to the LLM, and then we try to evaluate that prompt. And so like we are moving from this kind of employment of prompting and evaluation to this kind of employment. Like first we are going to choose the task, and then we are going to choose the appropriate prompting strategy for each and every sample of the task, and then we are going to give that prompt to the LLM, and then we are going to evaluate. So we are making a paradigm shift of uh, evaluation based on prompting evaluation based on prompting to evaluation based on task selection. So I just tried to show what are the flaws and what are the limitations of the current uh, employed techniques of evaluation as well as prompting. And now I think I will start with our work and the significance of our work and how does our work really overcome these limitations. So going further, so we are introducing hierarchical prompting taxonomy. So we are providing a set of rules to evaluate different prompting strategies as well as evaluate different tasks across different LLMs. So on a three-dimensional scale, you can compare the performance of any data set over any LLM using hierarchical prompting taxonomy. Rather than saying using hierarchical prompting taxonomy, using hierarchical prompting framework, which is employed by the rules of hierarchical prompting taxonomy. And one more thing, by that time you must have gotten it out that uh, how are you going to compare different tasks? Like, let's say you are going to solve some question answering task as well as trying to translate sentences. So if you want to really get an estimate of how an LLM is really solving these things, you try to use accuracy in question answering, and you try to use some kind of rogue score or blue score for getting the performance of output for translation tasks. So how are we really going to compare these two different tasks? I guess definitely we are not going to do them by using accuracy and blue. I think some new evaluation metric needs to be introduced so that which can assess the capability of different LLMs in solving different tasks. So here comes HP score. So we are introducing a new evaluation score called HP score, which can provide a better comparison of capability of solving a task by any agent. So I would like to highlight the point that by any agent because uh, this hierarchical prompting taxonomy not only evaluates the performance of an LLM over a task, but also of humans. I think I will discuss about that in the later sections of the slides. So yeah, moving further, you can see a diagram out here which tries to show the rules of the taxonomy and the employed framework out here. So the rules which you can see out, which are like basic recall and reproduction, understanding and interpretation, analysis and reasoning, application of knowledge and execution. So I guess, uh, like if you think in a cognitive manner, like we humans generally have these four kind of, we generally perform based on these four kind of rules to solve our daily reasoning tasks or to solve our daily tasks. So we thought, why can't we employ a similar set of rules uh, for solving, or for tackling the tasks by an LLM? So we have employed four set of rules which are pretty wide to cover any task which can be solved by an LLM. And we are choosing the levels of the prompting strategy here, which are employed and which are highly governed by the rules of this taxonomy. So the highest level prompting strategy out here is generated knowledge prompting, and the least level prompting strategy is role prompting. So our framework generally tries to say that generated knowledge prompting will be using a much more performance of all these four different rules. So generated knowledge prompting really requires greater amount of external knowledge, and it requires greater amount of analysis and reasoning, and it requires interpretation of external knowledge and by the LLM, and it requires interpretation of the relation between the input prompt and external knowledge. Let's say if you come to the case of role prompting, it is just like you are just assigning a role to LLM to solve a task, which barely requires any of these four rules. So I think you can understand that as we move down the framework out here, the prompting strategies have a strong influence by four of these rules. And you can see here uh, prompting selection strategy. And I guess one of them is manual and one of them is adaptive. I think like by far, like by the names given, I think you might have guessed that one thing is like uh, the prompting strategy is going to get selected manually, and the other thing is like an LLM is going to choose the prompting strategy in the other case. So yeah, moving further. So here I would try to show the hierarchical prompting framework, which was already shown in the previous slide also. So this is whatever framework which you're seeing in the blue color highlighted region. It's a hierarchical prompting framework. So yeah, like in our work, our HPF comprises five different prompting strategies, starting from least to most, like starting from least complexity to most complexity. So role prompting is the least complex prompting strategy, and generated knowledge prompting is the most complex prompting strategy. So moving further, so how are you going to evaluate, or how are you going to pass a prompt to an LLM based on this HPF? So the rules of the criteria, or like whatever rules which you have made in the hierarchical prompting taxonomy, are going to have stronger influence as we move down the levels of the prompting strategy. Let's say I've just shown you an example here. So let's say we are having a task like question answering task, which is having some prompt out here. So in our case, it's bull queue. So let's say you try to answer like is Delhi the capital of India? So whether it is yes or no. So rather than selecting a prompting strategy or selecting a complex prompting strategy directly, what the current like that's how the current in like that's how the current most of the works does. But what we try to do is we try to iterate over the levels. So once we have a base prompt, like once we have the question, and we try to directly inject that question into the role prompting first, and then we'll pass that role prompt into the LLM. And like if you are really able to get the answer correct at level one, we are going to stop the evaluation right here and move to the next sample of the data set. Let's say for the second question, the LLM was not capable of solving the question or getting the right answer at role prompting. So we move through the next level and try to solve it with the zero shot chain of the prompting and see whether an LLM can solve it or not. And if the LLM was unable to solve or unable to get the right answer even at level two, then we try to move to level three and try to get the answer. And like if we are going to get the answer, like get the right answer at level three, then we are going to exit from the evaluation of this sample and move to the next sample. So this is how the manual HPF works. So we manually iterate from lower levels to higher levels until we get the right answer. And I guess like you guys might be having the doubt, what if an LLM might not get the right answer even after 5 levels? So I think I will show how we are tackling that problem in the next slides. So yeah, these are the 5 prompting strategies employed in our work. So role prompting, prompts that define a role for the LLM in solving a task. So generally we used for solving question answering task, we had role played the LLM into kind of omniscient person. And for solving reasoning tasks, we had role played the LLM into a critical thinker. And for solving translation tasks, we had assigned a role called translator to the LLM to get best or to get superior performance out of LLM. So, and if you go to the zero shot chain of thought, which is pretty popular, so we just appended let's think step by step after the base prompt of all the use cases which we are using in our work. And yeah, it's general with three shot chain of thought prompting. We will be having three examples before the base prompt. And if you've heard of least to most prompting, which is not very quite popular compared to chain of thought prompting. So least to most prompting is similar to chain of thought, but it never really provides examples. It tries to dissolve a single prompt into different prompts and tries to extract knowledge from sub problems and try to derive essential insights and finally solving the final problem to get the answer. And generated knowledge prompting, so prompts that require the integration of external knowledge to solve your task. So in our case, we are using Llama 3 8B to generate the necessary knowledge. So we have tailored prompts to generate the knowledge from Llama 3 8B relevant to the task which is solved by the other LLM which is being evaluated on. Let's say we are evaluating 5.3 mini model on question answering task. So if the HPF goes until GKP prompting, like generated knowledge prompting, so the base task will be given to Llama 3 8B and it tries to extract the knowledge, and then whatever knowledge gets extracted, it gets integrated into the uh, original prompt and then inferred over 5.3 mini. So actually there is some more modification out here. So we try to extract three different knowledges from Llama 3 8B, and once after extracting three different knowledges, we try to choose the knowledge which is having highest confidence score from Llama 3 8B. Let's say if you're having knowledge statements K1, K2, K3, and if K3 is having a knowledge score of zero point 0.8 compared to other two statements of K1 and K2, we are going to choose K3 and integrate it with the original prompt and then infer it with 5.3 mini. So yeah, moving further, like now I think it's time to like say the difference between manual HPF and adaptive HPF. So yeah, I guess like I have already spoken about manual HPF in the previous slide that we are going to iterate over the lower levels to the higher levels manually and see whenever we are going to solve the task, and like we are going to stop out there and move to the next sample. So like by manually traversing each level, like it ensures that every potential strategy in our model or in our HPF framework is explored and allowing the LLM to like identify the most effective prompting strategy to solve that particular example of the task. Let's say if you're solving IWSLT data set, so and for some sample it feels that role prompting is the best, so it solves it role prompting directly. But I guess like we can, rather than manually iterating, so selecting a prompting strategy compatible for the task is also a task itself. So I just don't want to make things confused. So I'm just trying to make sure that uh, like if human is trying to do out some prompt engineering and try to tailor the prompt to get the expected performance from an LLM, the prompt engineering itself is a task, right? So why can't we really automate it using an LLM and see the scores of see the HP scores of that task? So this is our idea. So like our idea was entirely based on automating the selection of prompting strategies also. So what we introduced is the adaptive HPF, where there is a prompt where we called a prompt selector, which is generally a LLM. In our case, it's Llama 38B, which is chosen as a prompt selector. So it determines the prompting strategy, which is most suited for a given task. And after the selection of the prompting strategy by the prompt selector, the selected prompt will be passed into the LLM, which is being inferred on. So like this allows us to examine like how LLMs can be utilized to assess their abilities to different tasks, as well as automatic their evaluation processes. So like recently many works are coming out like uh, how LLMs are being used as a judge to evaluate the models. So we are playing our part in, rather than just using LLMs as a judge to evaluate the models, we're also making the LLMs also to choose the prompt and evaluate the models, because I think both prompting and evaluation always go hand in hand. And so here comes the thing like HP score for datasets. So like I think if you ever remember in my previous slides, I had tried to mention that like this framework also assigns HP score for humans also. So what we had tried is we have tried to give a comparison between how LLMs and how humans can solve these different tasks. So a task lower HP score indicates the more capability of solving the task, which is pretty contradictory to most of the other metrics. I think you keep a note out here that if a model, if an LLM is able to solve a task with lower HP score, the capability of that LLM in solving the task is pretty high. So for evaluating the data sets, we have chosen 5% of our of the original evaluation size, and tried to scale each and every sample of the representative set on a scale from 1 to 5. So we are choosing 1 to 5 because to maintain normalized scores across all manual HPF and data sets and adaptive HPF. So in our case, our HPF only have 5 levels of prompting. So we would be scaling each and every 4 rules of HPT on a scale of 1 to 5, and then we are going to take mean of that. So that's how each and every sample is going to get scored. And once we score each and every sample of that representative set, we are going to take mean of all those samples to get the final HP score of the data set. So I guess you can here see the scores of pool Q, CSQA, IWSLT, Samsung. So pool Q is a question answering data set. CSQA is common sense QA data set, I guess, which is pretty popular in reasoning tasks. And in IWSLT is a translation data set, and we have specifically chosen English to French translation. And Samsung is a summarization data set by Samsung. So by seeing the scores out here, you can find out that humans like have found it easy in solving Bulk, and they found it CSQ as the most complex task in solving. So Bulk is the most easiest task to be solved by humans, and CSQ is the most toughest task to be solved by CSQ. So moving further, so yeah, we are having 5 levels of prompting techniques in our framework, and each level has a score which is equals to X. And I had raised a question that what if an LLMs fail to address a task at all levels of prompts, like even after 5 levels, if it was not able to address the prompt, so how are you going to penalize it? So uh, so we can't have a common penalty for all data sets, right? Because that can never really give a comparable performance across all the data sets. So whenever some sample cannot be solved by an LLM after all the 5 levels, it gets penalized by M levels plus the HP score of that data set. So let's say some sample of polycode data set is not going to be is not getting solved after 5 levels. So we generally penalize it with 1.71 plus 5. So the penalty is 6.7 for that sample. For example, if the sample is going to get solved at lower levels of prompting, so I guess like we are going to just assign the level score. And once after we are going to get all the scores of all the samples in that particular data set, then we're just going to take out the mean to get the final HP score. So this is how we are calculating HP score for manual HPF. And coming towards adaptive HPF, so one thing we should keep out an eye out here is we are making a LLM to choose the prompting strategy, and we really can't say that the prompt selector or the LLM will definitely choose the best prompt strategy in one iteration. Because let's say to solve some sample in manual HPF, that sample can be solved in role prompting itself. But if you try to uh, do the same sample in adaptive HPF, in the first iteration of the prompt selector may give that like the prompt selector may think that uh, generated knowledge prompting is the most suitable prompting strategy, so just go and apply it. But I think uh, it's not really the most suitable prompting strategy. I think role prompting is the most suitable prompting strategy. But our main agenda of adaptive HPF is like, can LLMs can really get role prompting rather than generated knowledge prompting in lesser number of iterations. So what we have tried to make sure is we are giving 5 iterations, 5 chances to the prompt selector to choose uh, the most suitable prompting strategy. So rather than just giving one chance and taking out the probability of giving the most suitable prompting strategy, so we are giving 5 number of iterations. So we are giving 5 iterations because a maximum number of iterations equivalent to the number of levels in manual HPF are provided. Because to maintain normality or to maintain normalization across all the scores or across all the frameworks. And here also the same thing. If some task or if some sample cannot be solved even after 5 iterations, let's say for some sample X, the prompt selector tries to provide level 5, level 5, level 5, level 5 repeatedly, and even after 5 iterations, uh, the inferred model, let's say we are inferring on 5.3 mini, so 5.3 mini cannot really solve it. So I think we need to penalize it. So we are having a penalty here. And yeah, it's the same thing. Once after we have all the scores for uh, all the samples, then we are going to put out find the adaptive HPF score for that data set. So yeah, moving further, we are using Llama 3 8P 53 53 mini, Mistral 7B and Gemma 7B uh, for our experimentation. And like we are using all of them in 4-bit quantized versions. And apart from that, to solve IW, SLT, and Samsung datasets, they really don't have a hard dead end, because if you go to the case of Boltzmann and CSQA, it is kind of the final answer is kind of binary. Either it will be true or false, either it will be any one of the options among the questions in CSQA. But that's not the case with IW, SLT, and Samsung. So we had tried to put out some thresholds over the performance of these datasets. So generally, like in our work, we try to evaluate the performance of each and every sample of IW result by blue score, and we try to evaluate each and every sample of Samsung by rogue score. So we try to put out a threshold of 0.15 and zero point 0.2 across both these scores. So putting a threshold means it's like we are expecting a performance of at least a rogue score of 0.15 for each and every sample of the dataset of Samsung by an LLM. That's what a threshold means out in this case. So you can see the diagram out here. So as I already said before, uh, higher the HP scores, lower is the capability of solving. So if you can clearly see that Llama 3 is having pretty low scores across all of the tasks and all of the thresholds, and Gemma 7B is having pretty high scores across all of the tasks and all of the thresholds. And I would like to show some more numerical data, quantitative data out here. So uh, you can see the bolded things out here. So if something is getting bolded out here, it's the best performing model over the dataset. So Llama 3, in solving all these datasets, it found out solving SAM 0.15 the easiest, because if you can compare all the scores of the first row, uh, the SAM with a threshold of zero point 0.5 is having the least HP score, which means that Llama 3 8P is more capable and it finds it much easier to have all the samples having a ROP score of 0.15. And if you are going to compare it vertically, let's say if you are going to solve bool Q across 4 different models, so I think Llama 3 8P is having the lowest HP score. So that means Llama 3 8P is more capable and is finding it more easier to solve the bool Q dataset compared to all other different models out here. And that's the same thing, but I guess like now we should see the evaluation metrics also, the normal evaluation metrics. So you can see out it's like we are reaching human level performance. Like uh, almost all of the samples are getting corrected, because like most of the accuracy is nearly 99. And coming towards the common sense QA, it's the same thing. Uh, Most of the accuracies mentioned in our paper are far better than the accuracies mentioned by the organizations like Meta in their model cuts. Uh, so I guess like employing our framework and employing HPF uh, would yield better performances over different tasks, and would also be making like would also be make better comparisons across models as well as across data sets. So that's what we are trying to do out in our work. So I just want to add one more thing out here. If you can clearly see that uh, common sense QA, which where humans found out the most difficult to solve, so it's 2.5. But you can see out here the 5.3, the smallest model among all of these things, found out easier to solve CSQL. And one more thing is, uh, all of these models are actually performing better than humans in solving both bool Q as well as CSQA if you can compare the HP scores. Because like the HP scores of solving bool Q and CSQA by humans is 1.71 and 2.52. And you can see that each and every sample, each and every numerical value out here is less than 1.72 as well as 2.52. And one more interesting thing which we observed is the smallest model of all is finding it easier to solve the toughest task even by humans. So yeah, so pre-training LLMs in domain with domain specific data adds great advantage, and that is shown clearly by our framework. So moving further, so you can see the results of adaptive HPF here. I think you were all quite astonished by the larger numbers out larger values of HPF scores here, which means a pretty degraded performance compared to manual HPF. So these scores clearly indicate that uh, the prompt selector was not able to select the best prompting strategy in the minimal number of iterations. So it is taking some time. It is taking its own time to get the best prompting strategy to solve the task. And similarly, you can see the the degradation of performance of the original metrics here. That indicates that uh, there is an increase in number of the samples which are not getting solved even after 5 iterations. That means like the number of samples which were not getting solved after 5 levels in manual HPF are far less compared to the number of samples which are not getting solved after 5 iterations by a prompt selector. So why is the prompt selector is not able to choose the best prompting strategy in the minimal number of iterations? So I think hallucination is a major factor out there. So hallucination of the prompt selector in selecting the best prompting strategy for some sample place, or is a major key factor in the degradation of scores, providing higher HP scores. And you can clearly see that uh, the trend of the accuracies is almost similar. It's not actually greatly varying uh, either in uh, either in BoolQ and CSQ or the normal IWSLT dataset and Samsung dataset. And one more interesting thing you must have seen here is that uh, even if we try to increase the thresholds from 0.15 to 0.20, the performance is not actually changing. So one interesting observation which we made here is all the LLMs are getting saturated after some expectation of performance by them. So we really don't know, or like we really haven't studied or we really haven't interpreted about it, but we're trying to do a future work over there. And yeah, I'm talking about hallucination and adaptive HPF. So you can try to mention out some 4 examples out here. Let's say in BoolQ dataset, like you're trying to answer a true or false question, so his out stacks and property tags are the same. But the Llama 3 tries to give level 4, which is least most prompting in level 1, iteration 1, but the model was unable to solve. Uh, the model can be anything, like it can be Mistral 7B or it can be 5.3 mini, whatever it be. And we move to iteration 2, and then again Llama 3 was giving level 4 repeatedly, so which kind of hallucinated. So we tried, and finally at the 4th iteration it tried to provide level 2, and the inference model was able to solve the task. And that's the similar case with BoolQ, CSQ, and all of the other data sets also. So this clearly shows that uh, even the most capable model, Llama 3 8B, according to our HPF scores, like once if you can compare both the manual and adaptive HPF scores, we had seen that Llama 3 8B is the most capable model and most generalized model in solving all the tasks. Even that was not able to select the best prompt to, or not able to decide the best prompt to solve a task. So I guess like we need to do a lot of work out here to make LLMs select the best prompting strategy to solve a task. And like we can make a similar analogy here. Like adaptive HPF is similar, simply tries to uh, the judge the task based on which it is getting evaluated on. So yeah, showing out the outcomes of our work. So adaptive HPF faces difficulty in solving the tasks when compared to both manual HPF and human experts as well. And one more thing is like which I have already spoken in the previous slides, that both frameworks have higher HP scores when solving IWSLT as well as Samsung. So they're generally having higher HP scores compared to domain experts. Uh, like this clearly indicates that mm, uh, pre-training LLMs with more domain-specific knowledge is needed to demonstrate better performance across domain-specific tasks. So I guess like the HP scores of these LLMs provides a better understanding or gives a better perspective whether to fine-tune a model or on a downstream task or not. I guess this can give a much more better and much more comprehensive view. When do we need to stop prompt engineering and when do we need to start fine-tuning over a downstream task? And as I talked previously, that uh, both the IWSLT and Samsung evaluation scores are getting saturated over some threshold. So that means like we really can't expect higher levels of performances over some threshold for all LLMs for some domain specific tasks. And like finally, our experiments demonstrate that different tasks really don't need sophisticated prompting strategies always, or different all LLMs doesn't really need sophisticated prompting strategies to solve each and every sample of the data set. So it greatly depends on the LLM's aptitude for the task. And moving on to the limitations. So yeah, we haven't tested out all the models in the industry right now. So we are very limited to the number of models, and that's the same case with the data sets as well. So yeah, like accounting us to the name that we are trying to provide a universal framework. I guess incorporating more different LLMs and more different data sets might provide us a better perspective and better uh, view about the HPT. And in the future, I think adding more prompting strategies and having different structures of manual HPF um, might lead to better performance over more generalized tasks as well. And as you guys have seen, that adaptive HPF is also not performing pretty good in selecting the prompts, which is kind of wasting a large amount of compute, which is definitely compute inefficient because it's having 5 iterations or having definitely more than 2 or 3 iterations for solving each and every sample of a data set is definitely computably inefficient. So I think we need to work out here, try to fine tune the prompt selector, or try to introduce ensemble techniques to enhance the efficiency and effectiveness of the adaptive framework. Yeah, and like concluding out here, so the HPT combined with HPFs offers a robust and like an efficient method for evaluating LLMs, which gives a multi-dimensional perspective or multi-dimensional comparison across data sets and across agents across LLMs. And so, yeah, our findings highlight the effectiveness of HPF uh, in evaluating the task with the most effective prompting strategies, as well as how can task complexity play its role in the prompting as well as in the evaluation. So moving on to the feature work, currently we are trying to understand the effects of quantization over the applicability of HPT. So we have used 4-bit quantization models. So we really don't know if we are really used the original 32-bit format. We might have get the correct answers even at lower levels, or the expected performance even at lower levels, which can result in lower HP scores. And as I had talked about in the previous slides, that we might need to uh, increase the structure or include more prompting techniques into the manual HPF might yield better results and generalized results, which can cater to a large number of tasks as well. And moving on to the next feature work, we are also trying to work on uh, synergized prompt routing with HPF. So generally, we route prompts to the most relevant model, which can solve it pretty efficiently. So rather than directly routing the prompt directly to the model itself, so first tailor the prompt based on the task complexity as well as the model performance, and then try to route it to the model would be a great thing, and it can save our cost, and it will also reduce the efforts of the end user to do prompt engineering to solve his tasks. So it's like generally we are moving from a prompt based query to task based query, which is judged by the router, or which is routed by the router to the model, which can solve the prompt based on task complexity as well as its model performance based on preference optimization by the router. And the next thing which we are also working on is prompt ensembling using adaptive HPF. So rather than just using a straightforward manual HPF, we are going to use 5 different prompting strategies across the 5 different prompt templates mentioned out here. And these 5 different prompt templates are going to judged out by the adaptive HPF, and then we are going to choose them. So rather than manually iterating out this stuff, fine tuning a judge kind of prompt selector to select the prompt might be a great fit in the future. And we are also working on adversarial attacks with HPT, and as well as fine tuning with HPF. That recently people are building data sets for fine tuning combined with prompting strategies. Like most of the examples in the fine tuning data set are like 3-shot COT or a few shot COT. So what we thought is like not every time you need to have prompting is same complex, the same thing. You need not have the same complex prompting strategy combined into each and every sample. So for building high quality data sets for fine tuning, you can employ HPF before the fine tuning stage to build out the prompting strategy injected into each and every sample. So that like sample one might have just the role prompting injected sample input one, and let's say sample n may have generated knowledge prompting injected into its input to input n. So these inputs, along with the prompts injected by the HPF, are going to get used by the fine-tuning model, which might provide better performances, because we are selecting the dataset, or we are choosing the dataset based on the capability of the fine-tuning model itself. So yeah, that's it. And yeah, thank you everyone, and thank you for giving me this opportunity to present our work.
Amazing.
I think, yeah,
Thank you so
I'm
much.
open to questions.
Thank you so much. Yeah, let's all give a big round of applause. That was really, really interesting. So yeah, you can do so with the little smiley face. Cool. Okay. So I can certainly ask a couple of questions, but first of all, any questions from anybody in the audience at all? Again, it can be a very simple, small question. It can be, you know, very basic or advanced, or anything in between. Yeah. Ivan, got a question? Or was that trying to applause? Sometimes we get a mix. Hey.
No, thank you for the presentation. It was very insightful. I just couldn't help compare the HPT architecture with that of LoRa, so low rank decomposition, and it also feels like a. So, any comments on the same from you? Because what LoRa seems to be doing is also tuning to downstreaming tasks, but instead of a hierarchical testing structure, it rather uses a tunable weight matrix. So yeah, I'd like to know if you would like to consider working in that direction. Thank you.
Yeah, I think the question you raised is pretty good. But yeah, like that's a different domain, I guess. So LoRa tries to optimize the way we try to fine tune the models, and what we are trying to do is we are trying to optimize the way we are trying to infer the models. So we are trying, both are quite different sets, both are quite in different domains of the same thing, but one caters to the inference and one caters to the fine tuning.
I guess both arguably can be for inference though, right? Like in one way you can be modifying the prompting template to try to make it task specific, and in the same way you can have one model that has many LoRa's, for example. So I know that it's quite often the case where if people are trying to expand the performance of a model to handle 10 tasks, that you can have like 10 LoRa's, and then you can kind of route between those LoRa's, and that's quite a common way of trying to kind of improve performance. So I guess there's some analogies to kind of routing across LoRa's or routing across different system, different prompting strategies, which can mean they're both relevant for inference. But yeah, I guess they're different approaches to the same thing. And I guess the prompting strategy works with proprietary models as well. Although you didn't test it with it, but you can do this stuff with GPT and Anthropic, whereas you can't do LoRa with those, of course. Well, maybe you kind of use my GPT.
I guess like our work is mostly based on like routing the prompts based on the task, I guess. And I think it seems
I didn't fully get it. Are you able to identify the task ahead of time then? Sorry.
Yeah. So basically like whenever we are going to evaluate, let's say we're having the question like is Delhi the capital of India? So is Delhi the capital of India injected into role prompting, and is going to get evaluated by the model first. So if the model is able to solve that sample in the role prompting stage itself, it's going to it's going to move to the next sample. But if it's not really going to get solved by that inference model at that time, we are going to manually or iteratively move to the higher levels and make sure that the LLM is able to solve that sample or not. So our main agenda is like uh, all even the samples within the data sets, like the LLM responds differently to each and every sample to the data set also. So that's our main agenda. Like some samples can be solved by pretty basic prompting like role play prompting, but some samples of the same data set cannot be solved by the same LLM. At role play prompting, it requires higher levels of prompting. So using the same prompting strategy for all the samples is not good, is not needed. So that's what we're trying to make.
But do you have cases where there are cases where a more sophisticated prompting strategy degrades performance as well?
Yeah, that's the case in adaptive HPF actually.
Yeah.
Because like in manual HPF, we never really move to the most sophisticated prompting strategy, which is generated knowledge prompting, until the model cannot solve the task in the lower levels.
But are there
But
cases where the model can solve the task, but the more sophisticated prompting cannot solve the task?
yeah, there are cases.
Yeah.
There are cases. There are cases. Even all the 5 different prompting strategies cannot solve the task, and that's where we penalize the sample. So that's where we penalize the sample with the number of prompting levels with HP score of the dataset given by the human experts.
Sorry, so you said there's cases where all 5 can't solve it.
Yeah.
But my point is there's cases where the really simple one can and the really complex one can't.
Yeah. Okay, I got it.
Does that happen?
Yeah, that thing also happened. That happened in adaptive HPF. Whenever prompt selected tries to select a higher level prompt, I had tried to show it in one of my diagrams. Like you had seen that Llama 3 selects level 4, level 4, level 4 iteratively for 3 iterations, and it selects level 2 in the 4th iteration. So the level 4 iteration cannot really solve the task, but level 2nd iteration has solved the task.
Yeah, okay, makes sense.
Yeah.
Was there a question there from, oh, maybe, I don't know if it was a mistake, but I saw a question briefly from maybe Nishant, but if it's a mistake, no worries. Any other questions? Yeah, is there a question from you, Nishant?
So thank you for your presentation. So I have a question. I am in this field, so I just want to know about the planety. What kind of planety?
What was that? Sorry, what? Say again.
I was also unable to get the question. Can you, I think your voice is quite breaking. Can you speak it out loud?
The planety. That's what I heard, something like this, but I didn't quite catch it. Just the word.
Brother, I am new in this field, so I just want to know about what you mean by planety. Planety means if a model is if a model is not able to answer at the level 5, so you are giving a planety. So what kind of planety?
I got it. So I think I just want to take out one quick example. Let's say you're trying to solve sample 1, and let's say we are having 2 samples, sample 1 and sample 2, and both of these are corresponding to some data set. Let's say you are trying to choose some model X, some LLM X. So sample 1 gets solved at level 5 by the LLM X in manual HPF. So we're going to assign a HP score of 5 to that sample 1. Let's say if you go to the sample 2 case, the model cannot solve the sample even after 5 levels. So it is meaningless to assign the same score 5, right? In one case, the sample will get solved at level 5, or assigning score 5. And in the other case, even the sample is not getting solved even after 5 levels. And assigning the same score 5 to both the samples can never really give a better comparison. So we try to penalize these kind of sample 2s. Whenever we try to get some samples like sample 2, which are not solvable even after 5 levels, we add a penalty score plus the original level score. The original level score is 5, and we try to add a penalty score of the HP dataset. We are having different penalties for different datasets because each having its own kind of relative performance. So having the same penalty for all kind of datasets is not meaningful. That's why, let's say if some sample is not getting solved after 5 levels in BoolQ dataset, we add a penalty of 1.71. But if the same sample of CSQ is not getting solved after 5 levels in CSQ dataset, we will be adding a penalty of 2.52. So these penalties are also based on their relative complexities annotated by human experts. So I think you got the idea.
Yeah, I think that was well explained. Yeah, thanks a lot, Devi. Okay, well, I think we'll have to wrap up. So there was one final point from Yara, which was instead of using a LLM as a prompt selector, do you try to use, let's say, a specific neural network architecture that you can link different prompt tasks according to the complexity of the task? Not sure if I missed something. Yeah, so I guess you could use other neural networks instead of the LLM as the prompt selector. Maybe a few very quick points on that, because then I also have another thing I need to jump to, and I guess we should try and be on the time. But yeah, any final points on that, Devi?
Yeah, I think that's what our future work lies in. I had already mentioned it in the adaptive HPF optimization.
Yeah.
We are working towards the things where we are trying to fine tune the adaptive HPF for make sure that adaptive HPF, the prompt selector always chooses the best prompting strategy in minimal number of iterations. And having a specific metacognitive model or fine-tuned model for that is the final answer for that.
Yeah. Okay. Really. So also a really great point brought up by Evam here. So, hey, Budagam, thanks for answering my question. May I add that the following resource to the discussion pool in the context of the case raised by Daniel that I raised, where a lower level prompt gets an accurate answer and a high level one doesn't. So there's a really interesting paper here, neural redshift, random networks and not random functions. So definitely something that we'll take a look at and maybe even include in the reading group, because this seems like very interesting. Infers the structure of the neural network is bigger determinant than the weights itself. Okay, very interesting. Yeah, thanks a lot for sharing, Evam. Maybe we can include this one in one of the reading groups. Okay, well, I'll let everybody get back to their day, but it was really amazing having you, Debbie. Yeah, really great paper. Thanks for going through all of that. And obviously, it seems like you're going to be doing lots more work in the space. So, of course, we'd love to have you again at some point in a few months to, present your next great work. But yeah, it was really great having you. So thanks a lot for joining us.
Yeah, thank you.
And have a great week, everybody. See everybody again, same time next week. Have a good week. Bye-bye, guys.
Bye-bye, guys.